Okay, so this is going to be our second to last topic that we're going to talk about with bonding, specifically covalent bonding, and that's going to be polar bonds and molecules. Okay, so we're going to be using periodic tables to figure out whether things are going to be polar or non-polar. Okay, so let's talk about something really quick. In ionic bonding, it's really easy to see who is going to become positively charged, our metals, and who is going to become negatively charged, our nonmetals. And this is directly because in an ionic compound, metals lose electrons and nonmetals gain electrons, okay? In a covalent bond, it's not that easy, right? Because in a covalent bond, we're not giving and receiving, we are sharing electrons, okay? So, covalent bonds, however, will differ based on who they're bonded to and who wants the bonds or the electrons more in the bond, okay? So this is going to be directly related to the electronegativity trend that we talked about during the course of the organization of the periodic table, okay? Kind of think about it as a game of tug of war, okay? Electronegativity is going to tell us who wants the electrons more. If their electronegativity is higher, that means that that atom in that bond will pull the electrons closer to it, where if the other atom has a lower electronegativity, they're kind of like holding onto that rope for dear life because the other atom is kind of pulling it towards them. Okay, so keep that in mind. So obviously a non-polar covalent bond is going to be when the electrons are being shared equally, okay? So this is especially going to be something like our Hofbrinkel atoms, so like hydrogen and oxygen. Let's think about this for a second. When hydrogen is bonded to hydrogen, hydrogen has an electronegativity, Hydrogen has an electronegativity of 2.1, okay? So the electronegativities are down here in this corner. Hydrogen has an electronegativity of 2.1. So if this hydrogen wants the electrons 2.1 and this hydrogen wants the electrons 2.1, they're going to share the electrons in this bond equally, meaning that they're going to have an equal distribution of the electrons, okay? A polar covalent bond, though, is going to be something when there is an unbalanced distribution of charge, meaning one atom in the bond is going to have a higher electronegativity than the other atom in the bond. So let's look at the example that I gave before, oxygen and hydrogen. And obviously, oxygen would have its electrons like this, okay? So let's look at this. Oxygen wants the electrons 3.5, where hydrogen only wants the electrons 2.1, okay? So this is going to be a polar covalent bond in favor to oxygen. So oxygen is actually going to pull those electrons closer to it. So it would be winning the game of tug of war, okay? So let's look at how we're going to decide whether we're going to be talking about ionic, which you know is metal and nonmetal, polar covalent, so unequal sharing, and nonpolar covalent. This is equal sharing, okay? In general, we're going to look at the electronegativity differences, okay? We're going to say anything where the difference is greater than 1.7, it's going to be considered ionic, okay? So most of the time, metal and a nonmetal. Polar covalent, we're going to be looking between 0.4 and 1.7 difference, and then this is going to be nonmetals not close on the periodic table. So for instance, oxygen and hydrogen aren't close to each other, therefore we would consider that being polar. And then nonpolar is going to be 0.3 difference or less, and this is going to be the same nonmetal, or they're really close to each other on the periodic table. Okay, so let's look at some examples here. Okay, so hydrogen and bromine. What I do is I look at my periodic table. Hydrogen's electronegativity is 2.1. Bromine's electronegativity is 2.8. So the difference is 0.7. Okay, so I'm going to look back on my table, and I'm going to be a polar, I'm sorry, you can't see that, a polar covalent bond because I'm between 0.4 and 1.7. So this is going to be polar covalent. Okay, notation. What am I going to talk about here? Notation deals with, okay, in ionic bonds, it's easy to tell notation, right? Because when an atom loses an electron, it becomes fully positive. When an atom gains an electron, it becomes fully negative, okay? And in a covalent bond, these atoms are not becoming fully positive and fully negative. Why? Because they're sharing electrons. They're not losing or gaining anything, okay? So I'm going to say if something has a higher electronegativity, since that atom wants the electrons more, their charge is going to become more negative than the thing that they're attached to. Okay, so let me say that again. And we're going to actually call this partially negative and partially positive, okay? So this guy, it's a lowercase delta, which is a Greek symbol, and delta means partially or partial, okay? And you have to know that partial means not all the way, okay? So whenever I see something like this with a negative charge, this doesn't mean fully negative, it means partially negative, meaning that side of the atom is going to be more negative, okay? So this will be partially negative or partial negative, where this obviously would mean partially positive. Okay? Okay, so let's look at this. Rule of thumb, this is going to be the higher electronegativity, and this is going to be the lower electronegativity, right? Because if somebody has a higher electronegativity, that means they want the electrons more, which means in a game of tug of war, they have more of the rope on their side, which equates to more of the electrons, okay? So again, if bromine has a 2.8, they're going to become partially negative, where hydrogen will become partially positive. So I will write it like this. I'm just going to illustrate my bond with hydrogen having a partially positive charge and bromine having a partially negative charge, okay? All right, potassium, chlorine. So automatically I should be thinking metal, non-metal, ionic, but let's do an electronegativity difference just to be sure, okay? So potassium is 0.8, chlorine is 3.0, if I see that right there, 3.0, so my difference is 2.2, okay? If I flip back to the other side, greater than 1.7 is an ionic bond, we were right, so this is ionic, and notation, potassium becomes fully positive and chlorine becomes fully negative, right? Because potassium is fully losing an electron and chlorine is fully gaining an electron, okay? Good. Let's do another one. Carbon and oxygen, okay? So carbon's electronegativity is 2.5. Oxygen's is 3.5. So my difference is 1.0. If I look on the next side, it's telling me that this is going to be a polar covalent bond. Okay, so polar, covalent, they're sharing their electrons. All right, let's see here. So I have carbon, oxygen. Who is going to be partially positive? It's going to be carbon because it has the lower electronegativity. It doesn't want the electrons as much as oxygen does. So this is going to be partially positive, where oxygen is going to be partially negative. Okay, I'm going to do one more that's a nonpolar, and then you guys can practice the rest. So bromine, bromine. This is going to be obviously it doesn't matter what their electronegativity is. There's going to be a 0.0 difference, which is going to make this a nonpolar, which means that there's no charges distributed throughout the whole molecule, which means that this is considered a fully neutral molecule, meaning it would just be something like bromine, bromine. Okay, so that is a polar, nonpolar, ionic bonds. In the next video, I'm going to talk about, okay, that's the bonds, but what does it look like with a molecule and telling whether it's polar or nonpolar?